In this problem, we're given a grid with n rows and m columns, and we will choose k of these squares and put a piece in each of them. Once we place these k pieces on the squares, this is considered an arrangement, and the cost of each arrangement is the sum of all the Manhattan distances of all the pairs. So what does that mean? Oops. So let's say we have a point at 0, 0, 0, 1, 1, 0, and 1, 1. The distance between this pair is 1. The distance of this pair from 1, 0 to 0, 0 is 1. But the distance from 0, 0 to 1, 1 is not root 2. It's going to be 1 because you go 1 down and then 1 to the right. So we only care about the offset of x and y. So it's offset by y by 1 and offset by x by 1. Right? So first let's read in n, m, and k. Okay. So first thing first, we can't just do this via brute force because that will take too much time. Because if we want to find the distance of all pairs, that'd be like O of n squared, and so O of nm squared, and that'll be too big, right? Because it needs to be to something to the at most something to the power of 1 times 10 to the 8, right? So let's just break this down to a bit more simpler issue, right? Let's pick one pair, right? Point x and y, and let's assume this is two of the k pieces, right? And so we fixed this pair in. So how do we choose the other k minus 2 points, right? So the number of ways to choose the other k minus 2 points would be nm minus 2 choose k, right? Because out of the nm points we fixed 2, so we're left with nm minus 2 points, and from those points we have to choose k minus 2 of them because again we fixed 2 of the k points, right? And we can do this for each pair. So for each pair there is nm minus 2 choose k minus 2 ways to pick the other points. So essentially for each pair we know that Manhattan distance occurs nm minus 2 choose k minus 2 times because it occurs in every in all of those nm minus 2 choose k minus 2 arrangements, right? So since that's the case, what we can, so let's say so we know pair 1 will occur nm minus 2 choose k minus 2 times, and then pair 2 will also, so just do this, whoops, yeah, and then pair 2 will also occur these many times, same for pair 3, same for pair 4, right? So the one thing we see in common is going to be this nm minus 2 choose k minus 2. So let's take that out, right? So we take that, whoops, nm minus 2 choose k minus 2 out, right? And then what we're left with is the Manhattan distance of P1 plus the Manhattan distance of P2 plus the Manhattan distance of P3 all the way for all the pairs that we have in this grid. So essentially what this problem breaks down to is we do nm minus 2 choose k minus 2 times the sum of all the Manhattan distances, of all the pairs in the grid, right? So we can do this fast enough, but we need a fast way to calculate the sum of all the Manhattan distances of all pairs in the grid, right? So we can actually do this in O of n time if we give it a pre-sorted list, right? So let's say we have the points, simple, right? Let's say 1, 0, 2, 0, 3, 0. So it's obvious that we have two pairs, this pair and this pair, So the distance of this pair is 1 and the distance of this pair is 2. So the overall Manhattan distance of all pairs is 3, right? Because it's 1 plus 2. Okay, but we looked at every pair on its own, right? But there's a faster way to do that. So let's break it into with x and y. So the y is always 0, so in this case y doesn't really matter. So let's break it into with x. 1, 2, 3, right? So the first pair is 1 and 2, right? So that distance is 1. Now we can look at the next 2 and 3, right? So we know the distance from 3 to 2 is 1. So essentially what we do is we use the sum that we get, the overall sum that we get to reach point 2, and then we add that to the distance from here to here times all the pairs prior to this point, so 2. So then this would be 1 plus, so the distance from 2 to 3 is 1 and the number of points prior to 3 is 2, right? So that's equivalent to 3, which is our answer, right? So what this breaks down to is we find the overall sum to reach the point before, and then we find the distance from the previous point to the current point here. And then we know the sum is going to be the overall sum to reach this plus the gap to jump from here to here times all the points before that. And by doing that, and if this list is already sorted, then we can do that in O of n. Okay, so let's try and do that. So I'm gonna make a function called distance to calculate the sum of all the Manhattan distances, right? So let's have our answer set as 0 at first, and then we'll have two vectors vector x and y, right? And so we'll have for I1 n plus 1, oh whoops, we need that, and then for 1 to m, then x dot pushback I, right? Because in our grid, our grid would be like 1 1 1 2 1 3 1 4 1 5, and then this would be 2 1 2 2 2 3, this would be 2 2 3 3, and so on and so forth, right? So what we do is what this does is this puts all the x coordinates of all the points on our grid into this vector x, right? And then using the same logic, this puts all the y coordinates in our grid into this vector called y. So now let's just use this method to find the overall sum with all the changes in the y, and then find the overall sum in the changes in the x. And as you can see here, we can do the x on their own and the y on their own because they are independent of each other, right? So first let's handle the x case, right? So let's have something called previous sum and set that to 0. And then for I between 1 and x dot size, yep, okay. We'll have our answer would be equal to it would be what, y, the current yi minus the previous yi multiplied by the number of elements that came before our current, and since we are 0 index, there'd be I elements before our current yi, and then we would increase this by the previous sum that we got. And oh yeah, let's have a const int mod, which is 1e9 plus 7. And then we mod the whole thing. And then ans mod equals mod to be safe. And then we have to change previous sum, which is going to be, we increase previous sum by this. And then we have to mod this, and then we just mod previous sum to be safe. Right, so this will find the overall sum of the changes in x for all the points in the grid. And so this focuses on the x coordinate, so we can basically use the we can use the exact same logic here to do it for the y coordinates. So let's set previous sum to 0 again. Then we go through all the coordinates in all the y coordinates. Then answer plus equals, oh wow, sorry, this should be xi. What am I doing? xi, and then this actually works out because I did this by mistake. Okay, yep, that works out. And then we would just return answer. So yeah, so I think this would handle calculating all the Manhattan distances. So we handled this part. Now we have to do nm minus 2, choose k minus 2. So the way we actually do this is, okay, so we need, let's also have something called max, which is 1e6 plus 50. Okay, 1e6 plus 15, I call that max. And then nlfac of size max times 2 and fin of max times 2. Okay, so then we calculate power in log time, so that would be LLA log B, LL result equals 1. So while B is bigger than 0, if B is odd, result equals result, result times A mod, and then we do A times equal A mod equal mod, mod equal mod, and then B divided by 2, and then we would return result. So this finds power in log of B time, right? So now that we have power, we need to write the inverse function to calculate choosing in a faster way. So let's just set E to be mod minus 2, R equals 1. So while if E is odd, then R equals R times X mod, then X equals X times X mod, then bit shift by 1, return R. Is that right? Yeah, that looks right to me. And then now that we have calculated the inverse, we can just do NCR, which is just going to take in long A, long B, and so if B is less than 0 or B is bigger than A, returns 0. Otherwise we would return fact of A times fin of B mod times fin of a minus b mod mod. Yeah, so this is a well-known way to find NCR in a fast manner. So now we just had to preset the values of fac and fin, right? So what we do is we initialize fac 0 as 1, and then for I between 1 and next times 2, fac I equals fac I minus 1 times I mod mod, and then fin of next times 2 minus 1 equals inverse fac of next times 2 minus 1, and then what is it? Yeah, it is for int I equals next times 2 minus 2, I is bigger than or equal to 0, minus minus I, then we would set fin I is equivalent to fin of I plus 1 times I plus 1 mod mod. So then, like we said above, it would just be computing the Manhattan distances of all the points on the grid, times that by NCR of n times m minus 2 and k minus 2 mod mod. Of course, there's a bug. Okay, previous sum. Oh, no bugs, okay. So this would be 8. Okay, that's not a good sign. It should just be simply 8. Okay, something's not working. So we read in nmk fac 0 1 I fac I equals fac I minus 1 times I mod mod fin nax times 2 minus 1 equals inverse factorial of nax times 2 minus 1 for I times nax times 2 minus 1 while I is bigger than 0. Negate I, fin I equals fin I plus 1 times I plus 1 mod mod, see out. Okay, so there's a loop somewhere. Okay, let's see if I messed up here. So if b is less than 0 or b is bigger than a, return 0. Return fac a times fin b mod times fin a minus b mod. Okay, that looks right. Inverse is mod minus 2 r equals 1 while e, if e is odd, r times equals x mod mod, x equals x times x. Okay, that's 8. Small bug. That's right. Okay, this is right. A, that's right. Okay, so just to go over the whole process again, we break this problem down into, we first fix 2 points, and then we realize there are nm minus 2 choose k minus 2 ways to pick the other points, which then means that these 2 points has to be in nm minus 2 choose k minus 2 of the arrangements. And what that means is that their sum has to be in nm minus 2 choose k minus 2 of these arrangements, which means we just have to find the Manhattan distance of this pair, and then we have to include that in nm minus 2 choose k minus 2 of the arrangements, and then so that basically breaks down into we find the distance, and that's in these many of these many arrangements. We find this pair distance, that's in these many arrangements, and the key thing to notice is that the number of arrangements that each pair is in is constant, so we can take that out. So when you take it out, all we're left is with the Manhattan distance of all the pairs in the grid, which is this. And so we just multiply this whole entire sum with the number of times each pair is in an arrangement, and that's how we get our answer. And this should hopefully work. Arrangement. Why do I struggle with that word? That should be good. Yeah, voila.